If you're running EM simulations, you already know that running the simulation itself isn't the hard part. It's the number of steps it takes before you finally click the run button. In this video series, we're going to show you how Nullspace can use AI to orchestrate that whole pipeline, and importantly, how you stay in the driver's seat the whole time. This first video in the series is the what and the why. No demos just yet. Today we'll put together the framework, which we'll build upon in future videos. Hello, my name is Ryan Cutshall, and I'm a Senior Applications Engineer with Nullspace. Welcome to episode 1 of the video series we're calling AI with Nullspace. The topic of today's episode? An introduction to AI orchestration. Before we dive in, a quick word on who we are. Nullspace builds full-wave, full-fidelity electromagnetic simulation tools for analyzing antennas and radars at system scale. There are 3 things worth knowing about when it comes to Nullspace. First, the physics is rigorous the whole way through. We solve Maxwell's equations directly. No asymptotic approximations are used. Second, it's proven on real hardware, more than 12 years of defense hardware validation with real products delivered to real defense programs. And third, it's built for modern computer systems, implementing both parallel CPU and GPU acceleration, plus our own proprietary matrix compression algorithm. First, let's deal with some ambiguity, because AI is one of the most overloaded words used in engineering right now. When people say AI, they might actually mean one of 3 nested but related topics. The broad outer ring is artificial intelligence, which is typically defined as a system that can do stuff that would normally require human judgment. Inside of that is machine learning, where systems can learn patterns from data. And inside of that is the topic that this series spends a lot of time talking about, large language models. These are nested networks that are trained on massive amounts of text so that they can then understand instructions and generate language. This text could be English, Spanish, Python, C++, or some combination of all of the above. The distinction between these topics matters because when we say AI in this series, we don't mean a surrogate model that approximates your physics. We don't mean a black box that spits out an answer that you can't check. What we mean is a language model that understands your goal and can drive the Nullspace solver, the mesher, and the post-processor step by step, or all in one fell swoop. The physics stays the physics. The large language model simply runs the workflow. So what then is LLM orchestration? Well, let's take a moment to talk more about that particular topic. First, it's not a surrogate model. A surrogate learns how to approximate your results so that it can skip the physics-based solve. That approach can definitely be useful in some contexts, but it's an approximation, and it's only as trustworthy as its training data. We're not doing that. Every result you see in this series comes directly from the real space method of moments solver. Second, it's not a generic chatbot that's bolted onto a menu. A general purpose assistant like that doesn't know anything about meshing requirements, material models, or some of the gotchas that make an EM simulation succeed or fail. Orchestration is all about guiding the process. This is the geometry creation, the mesh construction, the solver setup and the execution, the post-processing, results validation, and finally the report generation. The large language model coordinates the entire simulation pipeline, and it uses domain expertise that we provide. Think of this like an orchestra. The large language model is the conductor, but it's not the one actually playing the music. The LLM doesn't replace the solver. It simply directs it. The domain expertise that the LLM is using is the key. This expertise lives inside of 2 buckets that we will define because you'll hear us saying them a lot in this series: agents and skills. An agent is a large language model taking action towards some goal, either autonomously or with you guiding it. Whereas a skill is a knowledge resource that the agent consults with to do a specific kind of task correctly. The way I like to think about it, the agent is the doer, and the skills are its reference library of books. A skill is just a human-readable text file that captures knowledge and best practices. For example, how we like to prep geometry, how we script a simulation, and how we like to generate a report. Every LLM session then uses that same validated approach, and it builds on the lessons that we've already baked in. You can also add new lessons to the skill manually or with LLM prompts. One detail that sometimes surprises people: the agent doesn't read the full contents of every skill at the start of a new session. The session agent simply scans the name and description of each skill that's available, and it only pulls in the full skill when it decides that that particular one is relevant to the current task. And if you want to force the agent to pull a skill, you can do that. You simply use a / symbol followed by the name of the skill, and that forcefully invokes that skill directly. Two things I want you to remember about skills. First, skills are plain text. That means that they're easily accessible. You can read exactly what the skill contains. And second, because they're text, they can be subjected to version control, just like code. Your favorite version control tool, like Git, can track each and every change. And this skill format isn't something proprietary that we invented. It's an open standard that the majority of popular LLMs now support. We've simply built our EM simulation expertise on top of it. Okay, you now know the two keywords, agent and skill. Let me next show you how they can be arranged to orchestrate the nullspace workflow. First, the main session agent, the agent you interact with when you first boot up your LLM, acts as a router. When you write a nullspace-related prompt, something with nullspace or NESM in the prompt, the router figures out what kind of problem this is and what mode you want to run it in, and then it hands the work off to a single specialist. There are 3 specialists, which are known as the domain agents. The antenna agent is for antenna work, obviously. Gain, directivity, pattern cuts, axial ratio, those sorts of things. The RCS agent is for scattering, plane wave excitations, monostatic RCS, and bistatic RCS. And the microwave circuit agent is for single or multi-port circuit simulations, where you can get insertion loss, isolation, and so on. Underneath the agent sits a shared library of skills, plus a foundation of domain knowledge. The specialist picks up whatever skill it needs and runs the job itself from start to finish. And that's the entire architecture. The session agent that points to the right specialists, the specialists then do the work, and finally there's a shared toolkit that they can all draw from. Everything you'll watch in the later video episodes is some path through that same framework. Here's what running the job actually means. The specialist agent drives a pipeline, intakes some sort of specs or requirements, builds or imports the geometry, meshes it, checks the mesh, sets up the solver, executes the simulation, does the post-processing and the data visualization, validates the results, and finally assembles the report. And notice that there are 2 checkpoints or validation gates. If one of these checks fail, then the agent doesn't just plow ahead. It routes back to the stage that caused the problem, fixes it, and then reruns the simulation. That's the part of this process that makes it trustworthy and fast. If you take one thing from this video, it's this. Automation here is a dial, not a switch. You get to decide if you want to orchestrate everything yourself, invoking each skill manually and reviewing each output as it's produced. This is what's called maximum control. In the middle, you can drive the judgment-heavy stages and hand the routine ones off. And on the other end is the fully automated process where the agent runs the whole pipeline in the background while you simply monitor the progression. Here's why that matters. The agent only automates the orchestration that a human could do by hand. The skills are the durable toolkit. You're never locked out of the room where it happens. You can be in the room at any stage, any time. Maybe you need to steer, maybe you need to debug, maybe to double check. The LLM orchestration simply lowers the effort, but it never takes away your control. So anyway, that's the model that we're working with. From here on out, every episode gets more hands-on with specific antenna and RCS models. In the next episode, we'll start as simple as it gets with an electric dipole. You'll see firsthand the thing that surprises most people. You actually don't need to write any code. You can prompt the LLM with natural human language, and it generates the model, the simulation, and all of the post-processing commands. After that, we'll look at a benchmark of Nullspace EM's accuracy with the NASA Almond RCS results. We will build a pyramidal horn from an imported step file, scale a single element into a full array, and finally hand the whole thing over to the LLM agent for the automated optimization routine. So be ready for more deep dives into LLM-driven orchestration of electromagnetic simulations. If that sounds useful or fun, subscribe so you can catch the next one. See you in episode 2.